Hello. Yeah, very well, thank you. So today we'll have a guest speaker. So I'll be joining for a while and then hello, Edward.
Oh. Am I able to share my screen? Oh yes, I'm host. I'm host now. Let me. Is that sharing? Vlad, I'm not sure if you're on mute.
Hello. Hello, yes. Hello, David. Yes, so we have a few people here today. I guess school holidays and some people are absent, but this is being recorded. So and we'll post it on YouTube. Thank you very much, David, for agreeing to take this webinar. So
not a problem at all. Thank you for inviting me. I'm very much looking forward to it. We've got a couple of participants. Do they normally contribute, or do they normally just watch?
They contribute in the chat normally.
Contribute in the chat. Excellent.
Yes.
Okay, so firstly, just a little bit of introduction. So my name is David Vaccaro. I am currently an assistant head at a school in Buckinghamshire. I'm a mathematician by background. I studied maths at Cambridge as an undergraduate and then did postgraduate research at Oxford, where I was a maths non-stipendiary lecturer, admissions tutor at St Peter's College, Oxford, increasingly many years ago. But I've always enjoyed teaching that, you know, the interface between school maths and university maths. Firstly, and the other thing I'd just say is just a big congratulations to you guys for signing up to this program. I've only been involved for the past sort of 3 or 4 weeks, but I've looked through the problem sheets and it's spot on, exactly the sort of thought-provoking questions that you need to do to strengthen a university application. I don't know if I've numbered all the questions, but I've got a few questions to do tonight. The early ones are just on some of the topics that are on the problem sheet, so increasing and decreasing functions, inflection points, which I want to say 1 or 2 things about, periodic functions. Then on the later sort of sections, you'll probably recognize the format of the questions here as coming from math papers. So I've got a couple of multiple choice math questions. And then all of that will serve as a little bit of a warm up to a long section B math question. And then that will serve as a warm up to a step 1 question. Step 1 questions, even for someone who's got quite a lot of experience doing step 1 questions like myself, the prospect of doing that live later fills me with a little bit of fear. But I did want to get up to step 1 questions because I think that they are the sort of gold, certainly for sort of maths applicants, they are the kind of gold standard, you know, and you know, I think if there was one thing I would recommend working on, I think step 1 problems are fantastic. Okay, so let's have a look at this first problem. I can't remember the problems on the problem, you know, the exact problems on the problem set, but this is a question about increasing and decreasing functions. So it says, how many integers a are there such that f of x equals x squared plus ax plus 2a times e to the x is a strictly increasing function on the real numbers? So I've been told earlier that you'll answer questions in the chat. What's your gut instinct of the best thing to look at in order to establish when this function is a increasing function? Is anyone going to be brave? Is anyone going to be brave in the chat? There is a message in the chat, and the chat is recommending that I look at the derivative. Okay, and absolutely that is what I'm going to do. What sort of function do I have? Well, I have 2 functions multiplied together. So, and I won't put this into the chat. I'm assuming people will recognize this as a function which is a product. So, because I'm being recorded, I'm going to write my product rule out nice and neatly. So the 2 parts of my product are this polynomial expression x squared plus ax plus 2a and my exponential expression e to the x. Why is this question a little bit more sophisticated than an A-level question? We should note, one of the things we need to keep a little bit of a track of here is what is a variable and what is a constant. So this constant, this parameter a is a constant. So the function is only a function of x, so x is the variable. Okay, so it's not at all unusual for people to sort of get confused and start to do some sort of weird product rule, for example, if they differentiate ax, but we just treat ax like a constant. So as I say, I'm being filmed, so I'm going to write this out nice and neatly. So I'll find the 2 parts of my product. So I'll find my u dash and my v dash and put them together to find f dash x, which is u times v dash So that's just this polynomial expression times EX, and then the U dash with the V is the derivative EX. Luckily, there's an EX term, so I can just combine everything together, and I'm just going to neaten it all up. To get this derivative. Okay, people were very good in the chat last time, and they told me the right thing to do. They told me to differentiate. Why? For what purpose? What condition do I want to establish about the derivative? And there's a question in the chat. Excellent. Okay, so Mia has said that we want f dash x to be strictly greater than 0 for all x. Okay, so fx is strictly increasing. Okay, if and only if f dash x is greater than 0 for all x in R. Now, this question, let's have a look at the derivative, because this question is a little bit more sophisticated probably than A level. So what we want to do is we want to establish when f dash x will be positive. So the first thing we can almost discount is this e to the x term. What do we know about the term e to the x in terms of its sign? Well, e to the x is, oops, I'm writing with the highlighter. E to the x is the exponential function, and that is always positive. So the sign of the derivative is determined precisely by the sign of the quadratic bracket. So again, we've got an if and only if relationship that f dash x is greater than 0, if and only if x squared plus a plus 2, that's a horrible 2, x plus 3a is greater than 0 for all x in R. And when you're laying these out, it's worth saying why, and that's because e to the x is greater than 0 for all x in R. So the sign is just determined by the first bracket. Any offers in the chat of what condition I need to look for to decide whether this quadratic expression is going to always be positive? Right, now someone said the discriminant, and very, very well done, okay? Again, just in the sort of like world that we're in with these sort of problems, these kind of problems require us to sort of change the hat that we're using to think of. So we're taking off the thinking about differentiation hat, and we're now thinking about discriminants. And it's absolutely right that we want the discriminant to be less than 0. Because we've got a positive quadratic, we know that the general shape is going to be like this, and the only case when it's always going to be positive is if the discriminant is strictly negative. So this condition that the quadratic is always positive is equivalent to the discriminant being strictly negative. Okay, now we just need to do a little bit of algebra. So we get a squared plus 4a, but minus the 12a. So I'll just go straight to negative a to a plus 4 is less than 0. Up to entirely normal, so it's going to be between the roots of this quadratic. I quite like using the complete square form, so I can write this as a squared minus 8a plus 16 is less than 12, which is equivalent to a minus 4 squared is less than 12. Now notice that we're only looking at integers, so a minus 4 is going to be an integer, so we're just looking for the integers whose square is less than 12. Okay, so we know that a minus 4 is in the set of integers whose square is less than 12. So that's going to be anything which is between -3 and 3. Once we get to 4, the square is 16. Okay, so we know that a is going to be one of the integers 1, 2, 3, 4, 5, 6, or 7. And notice that the question said it only asks for how many integers there are. So that's 7 integers. So initially 3 negative ones, 3 positive ones, and 6.
Someone don't feel too good.
Of so yeah, very excellent. So there was a question of, could I show that the minimum is greater than 0? So I could have indeed differentiated and then found the value of the quadratic at the minimum. And just to show you that, because I think it's quite emblematic of this course and indeed emblematic of mathematics generally, I'll do that in the general case. So if I have ax squared plus bx plus c, and for it to have a minimum, I'm just going to say a is bigger than 0. How would I find the x coordinate of the minimum? So I would differentiate and look for where the derivative is going to be 0. So at the minimum, y dash equals 0. And so therefore at the minimum, x is equal to negative b over 2a. Now, if I was to find the y value at negative b over 2a, so at negative b, at x equals negative b over 2a, y is equal to ab squared over 4a. Take away b squared over 2a.
Sorry, Thomas, could you mute your microphone, please? Or
which is equal to c. Sorry, this is 2a squared, which is equal to c take away b squared over 4a, which is equal to 4ac minus b squared over 4a. Okay, and this is where maths suddenly, this is why we all like maths, because this term on the top of the numerator, so this is the y value at the minimum. This term on the top of the numerator is exactly the discriminant that we know and love. So what we have here, proved by calculus, is that the value at the minimum is positive. That's horribly written, sorry. If and only if 4ac minus b squared is bigger than 0, which is equivalent to the discriminant, which is equivalent to the discriminant being less than 0. Okay, so it's very much, in answer to the person who put in the chat, could we just look at the value at the minimum? It's very much an either or. Okay, so in this line here, in the working on the left, I found the value of the discriminant and set that to be negative in order to guarantee that my quadratic function here had no roots. But there's a nice little theorem, which is that the value of the minimum is positive if and only if the discriminant is negative. So you could easily have done, used calculus as well. Just try and make things a little bit interactive. Let's take a vote. Okay, so who would vote for this yellow method on the right of just finding the discriminant, and then who likes this calculus approach on the right of finding the y value at the minimum. So just write in the chat either discriminant or calculus, and we'll see what how the vote goes. So lots of people contributing to the chat. Oh wow, we have 1, 2, 3, 4 calculuses and only 1 discriminant. Well, I'm going to vote for the discriminant as well. I like using as low tech things as possible, and I would consider discriminant to be slightly lower tech and probably slightly less working. But then again, you guys do a lot of calculus, so liking calculus is not a bad thing at all. Okay, does anyone have any questions about that question before we move on? Okay, if everyone is, it's always nice to get a little bit of feedback. If people just put a thumbs up and say that they're happy, happy both with the question, with the pace, with the way I'm going through things, that would just give me a little bit of confidence. I'm happy to go through things a little bit quicker, a little bit slower. But everyone's happy, good. Okay, let's have a look at this question. So it says, let fx equal x cubed plus 12x squared plus 3x minus 5. And then it says, if a and b are constants such that the inflection point of the curve y equals f of x minus a plus b is the origin 0, 0, what is the ordered pair AB? So first of all, okay, how are we going to find the point of inflection of this cubic graph? So what is the condition that is satisfied by a point of inflection? Good. So someone has said that at a point of inflection, the second derivative is 0. Can anyone give me slightly more detail about a point of inflection? Is every point where the second derivative is 0 a point of inflection? So who thinks yes? Okay, so I'm going to put a question into the chat and just answer if you think yes or no. So if f double dash x equals 0, is x always a point of inflection? And even before I answered the question, someone has said no. Someone has said no, e.g. y equals x to the 4. Okay, so what? So for y equals x to the 4, the second derivative is 12x cubed. So the second derivative equals 0 at x equals 0. Why is that not a point of inflection? What type of point? What type of point do we have at x equals 0 with the curve y equals x to the 4, x and a minimum? So what extra condition do we need? What extra condition do we need in order to guarantee that it's a point of inflection? Okay, so Josh has said that one requires f dash x equals 0 and the function stay increasing and decreasing. Now that is certainly true. That what is true is that if you have a point like this where f dash is 0 but the function, the derivative does not change, this is a point of inflection. Okay. But is every point of inflection of that type? Right, excellent. So I'll just read the comment from the chat. So Mia from the chat has said that it's a point of inflection if the curve changes from concave to convex or vice versa. Okay, so I'm just going to work on my OneNote a little bit. I'm just going to introduce a little bit of space because I do want to go through this. I'll do it here. Okay, so firstly, so my question is, what is a point of inflection? And I've got this wonderful answer, which is it's a point where a curve changes from concave to convex or vice versa. Okay, so here is a concave function. Here is a convex function. I'll just tell you something silly. This is something silly that someone once told me to remind myself which is which. So the concave side looks a little bit like a cave. If you imagine a little bear living in this curve here, then this is the concave part of the curve, and this one is a convex curve. Right, that is the shape of a convex curve, and I've drawn them increasing. You could also think about what they look like when they're decreasing. What is the kind of calculus condition of when a curve is concave? Now, I always like thinking of this in terms of cycling. So if you were cycling on this hill as a cyclist, what would you say about the experience of cycling on this hill, on this concave part? Right. Okay. So Mira said that as a cyclist, you would say f double dash is x is less than 0. Okay. Now maybe if two mathematicians cycle, that's what one cyclist says to another. But what's that in more normal English? So in more normal English, on this concave part of the curve, it's going uphill, but both parts are going uphill. Now, what is the difference between this red part, which is going uphill, and this yellow part, which is going uphill? So this red part, which is going uphill, but it's getting less steep. Excellent. So here we've got getting less steep. Okay, so that's the low-tech definition of concave. That's the same as saying that the derivative, so the steepness, or f dash x, is decreasing. And we know that a function is decreasing if its derivative is negative. So this concave curve has got negative second derivative. This yellow part of the curve, the shape is opposite. Okay, it's getting more steep. Which means that f dash x is increasing, which is the same as saying that f double dash x is greater than 0. So at this point when everything changes, okay, this is the point of inflection. Now, in terms of cycling, this is actually relatively rare. What's more common for a hill, if you're sort of climbing in the Alps or something like that, is that to start with, the hill's quite flat, then it gets steeper, then it gets steeper, and then at some point you're running out of breath, but there's a nice moment when you can just suddenly feel that it's starting to get less steep. Okay, and so this is a point of inflection, which is slightly more common for cycling. When you go from convex to concave. Now I've drawn increasing functions, and you can think about what they look like for decreasing functions. So going back to the chat, does anyone want to now give me a watertight definition of what it means to be a point of inflection? So which covers real points of inflection, but excludes things like the minimum in y equals x to the 4. Excellent, yeah. So when f double dash x passes the x-axis, yeah. So when f double dash x changes sign, so when it goes from positive to negative or negative to positive, okay, and that guarantees that it will be an extreme value of f dash x. So it'll be the steepest point on the hill. Excellent. So that was worthwhile, I hope, but that's a definition of what this point of inflection means. So we're looking for this cubic graph for our point of inflection. We're looking for a point where the second derivative is 0, and we should also have in the back of our mind that it's a point where the second derivative changes sign. So let's go ahead and do that. So our cubic is f of x equals x cubed plus 12x squared plus 3x minus 5. Our first derivative is 3x squared plus 24x plus 3. Our second derivative is 6x plus 24. And so f double dash x is 0 when x equals -4. Does the second derivative change sign? Well, we've got a nice linear function. Okay, so f double dash x changes sign. Okay. Notice that this is a cubic graph. Okay, so a cubic graph will typically have a maximum, then a minimum, and then go up. And what you can tell from my cubic graph, if it's a positive cubic, is that it starts off looking like this, which is concave, and then changes to something that looks like this, which is convex. Okay, and you should be able to reassure yourself that the second derivative goes from negative to positive, which this expression clearly does. Okay, we need the coordinates of the point of inflection, so we just need to substitute -4 back into here. So f dash -4 is -64 plus 48, take away 12, take away 5. And so that is -16, -28, -33. Okay, so my I'll do it on my cubic here. My point of inflection is at -4, -33, and this is y equals f of x. Let's look back at the question. It wants me to obtain a new function where the point of inflection is at the origin. So what would people's suggestion be? And you should be able just to do this in the chat. What values do I need for a and b to move this point of inflection to the origin? You should get start to get things coming through in the chat. So what direction do I need to shift the curve? Okay, I've got a vote for 4 and negative 33, but we need to be careful that we need to be shifting it. Oh yeah, we want to shift it 4 units to the right. Yeah, so it is indeed f of x take away 4 plus 33, and that will translate this. That will translate this to the origin. What sort of symmetry do you think that translated curve will have? So the new curve will have its point of inflection at the origin, and it will be some cubic. So it'll be y equals x cubed plus some new coefficient of x squared plus some new coefficient of x, and then plus 0 because it's going through the origin. What can you tell me about the value of a x? And so it'll have. Okay, I'm just going to check a couple of things. So yeah, the suggestion is it will have rotational symmetry of 180 degrees, and that's absolutely right. Okay, and the reason for that is that the second derivative will vanish at the origin, and the second derivative will just be 6x plus 2a, and then because this is 0 at the origin, we have a equals 0. So my translated curve will only have an x cubed term and an x term, so it will have an odd symmetry. And I've had a suggestion in the chat that this is wrong. Negative 4 cubed is negative 64, plus 48, take away 12. Does anyone who disagrees? Have I made a mistake? I seem to be getting negative 33, but some people are saying that it's negative 111. Ah, well spotted. Yeah, well done, well done, well done. It's 12 times x squared. So it's 12 times 16. I did 12 times 4. Sorry, so this is 12 16. So this is 192. And so this is plus 111. And so this is negative 111. So I got everything right. I got everything right apart from the answer there. One important observation is what I've also shown, and you can turn this into a general proof, that every cubic function has an odd symmetry around its point of inflection. Okay, question number 3. I'll do this a little bit more briskly because I'm keen to get on to the later questions. So it says, if f dash x equals 1/4 x4 minus 7/3 x cubed plus 15 over 2x squared minus 9x plus 2, how many inflection points does it have? So let's first of all find the second derivative. So that is x cubed take away 7x squared plus 15x take away 9. I can see that x equals 1 is a root, so x subtract 1 is a factor, and I'll just do this in my head. So we get x squared. To get negative 7x squared, we need a negative 6x, and then we need a plus 9. So we get x minus 1, and then we get x minus 3 squared. So there's f double dash x is equal to 0 at 2 points, at x equals 1 and at x equals 3. Are both of these points of inflection? So put in the chat which one you think is a point of inflection. Okay, so people are saying no, they're not both points of inflection. Which one is a point of inflection? Yeah, only the x equals 1 is a point of inflection, because if I look at the sign of f double dash x, it starts off as negative, okay, which means that the curve is concave. It then changes, the second derivative changes to positive, but the second derivative does not change sign at x equals 3, so it stops being convex. There's a nice little task here which says to sketch f of x if f of 0 is 0. So it's basically integration without integrating. So I've been given the derivative function. I now want to reconstruct the function. So the derivative function is, the leading order term is x4. So for large negative values of x, the derivative is going to be positive. So the function is going to look like doing this. The derivative is going to decrease and decrease and decrease. When x is 1, the derivative turns out to be negative. Okay, so what happens to the function is it must have a maximum somewhere. Okay, now without doing sort of numerical tests, it's hard to know whether that maximum is positive or negative, but it must have a maximum. Then at x equals 1, that's when it's got the minimum negative gradient. From that point on, f dash x increases, and then it's convex. And then at x equals 3, it's kind of temporarily not convex. Okay, because it's getting less and less convex. But after x equals 3, it's convex again. Okay, so the x equals 3 isn't a special point. It's just a convex section followed by a convex section. But the point of inflection is here. Okay, and what we'd expect to see is a maximum at some point to the left of x equals 1, and then a minimum at some point to the right of x equals 1. Where those maximums and minimums are would require us to solve this quartic, which can't be done easily. Okay, I scampered through that one a little bit, but I did want you to see an example where the second derivative vanishes, but we don't have a point of inflection. Okay, are people happy with those 2 questions about points of inflection? If so, put a thumbs up in the chat and we can continue onwards. People are happy. Excellent. I wanted to now look at something else which comes up on the problem sheet. I wanted to have a look at an example of a periodic function. So the question asks for the fundamental period of f of t when f of t is the modulus of sine t plus the modulus of cos t. So put it into the chat what is meant by the fundamental period? Is anything coming into the chat? No. Okay, what is meant by a period? Okay, so right. Great, we've got a good answer from someone who says the fundamental period is the first time that the function repeats. Okay, and I think that's got the two elements of being the fundamental period. So can anyone give a really precise definition about what is meant by a period? So A is a period if and only if what? Excellent. F of x equals f of a. Sorry, f of x plus a is equal to f of x. So what that means is that the function does something between 0 and a. Okay, I'll do it like a heartbeat, a small loop and a big loop. And then at a, if you shift on a, the function then repeats. So this is a definition of being a period. Okay. But what's the difference between any old period and the fundamental period? It's the smallest period. Excellent. So in this example, so if A is a period, can anyone tell me something else which is also a period? Yeah, 2A. Yeah, because it obviously also repeats at this point, because from 2A onwards, you just get the same repeating cycle. Anything else would be a period other than 2A? Yeah, NA, where n is an integer. Okay, and I'll leave that as something to prove that any multiple of the fundamental period is a period, and conversely, anything which is a period is a multiple of the fundamental period. So for this question, to find the fundamental period, it actually breaks down into two things. So to find the fundamental period, we need to A, find a value of A such that A is a period. But then we also need to justify that our A is the smallest of all periods. Okay. I suppose, so question, what method do you think would be a good method to use to try and get a feeling for part A, to try and figure out what is a period? Or maybe spend a little bit of time scribbling with a bit of paper to try and come up with a value which you think is a period for this function, modulus of sine t plus cos t. And then we'll work on part B and try and justify that the period that we found is actually the shortest of all periods. Okay, I've thrown out some questions. I'll throw out the first question of all. What do you think would be the best method to employ to try and pick up some understanding of what's going on here? Right, brilliant. Graph it, sketch it. Okay, so I'm going to graph the function sine t. I'm hoping this is roughly familiar. What's different between the modulus, so to go from sine t to the modulus of sine t, wherever the function becomes negative, I need to flip it up and become positive. So this black function here is y equals modulus of sine t. Modulus of cos t is a similar sort of thing. Okay, but the section where cos t is negative is between pi over 2 and 3 pi over 2. Right, what I'm going to ask you to do now is to visualize what happens when you add these two functions together, the black function and the purple function, and in the chat suggest a value which you think is a period. Okay, so okay, we've got a suggestion in the chat for a period. We've got a suggestion for as pi over 2 as a period. Well, let's see why. So for the first pi over 2 range of pi over 2, the black curve goes up and then the purple curve comes down. In the next interval of pi over 2, the purple curve goes up and the black curve goes down. Now, what I hope you can see, and maybe I want to change my colors a little bit, is that this purple curve going up here is exactly the same as this black curve going up here. Whereas the two curves that go down in the same way. Okay. So from my visualization, now I don't know about you, but I don't think that without the graph, I would have picked pi over 2 as a period. Okay. But from the visualization with the graph, I think that pi over 2 is going to be a period. Okay. Let's try and prove this. So you could prove this by trig identities, but you should just be able to tell me just from looking at the graph. Can anyone give me a simplified expression for sine of t plus pi over 2? Okay, so we've drawn our sine wave. We've reached pi over 2, and then we're looking at what the sine wave does after that. Or alternatively, we're thinking of shifting our sine wave back by pi over 2. What does our sine wave become? Cos t. And what is cos t plus pi over 2? So we're just doing a similar thing with our sine wave. Cos wave, sorry. We're drawing a cos wave, and then we're starting at pi over 2 and then thinking what the cos wave does afterwards. So this section of the cos wave is this section of the cos wave is what we get after pi over 2, and that's just an upside down sine wave. Now, if we take moduluses, the modulus of sine t plus pi over 2 plus the modulus of cos t plus pi over 2 is just the modulus of cos t plus the modulus of negative sine t, but the modulus just gets rid of the negative. So we just get cos t plus sine t, and even though the order has changed, that just gives me f of t back. So f of t plus pi over 2 is equal to f of t. Are we done? Have we finished the question? No. And why have we not finished the question? Because we need to show that it's the smallest period. So we need to show that no smaller number will work. Now, a very good thing to look at is, let's try and, we know that the overall function starts at 1. So if we could show that the first time my function is ever 1 is at pi over 2, then we would be done. Okay, so what I'm going to look at is I'm just going to look at the function between 0 and pi over 2. And if I can show that the function is never 1 in that interval, then I would know that nothing that's smaller than pi over 2 would work. Now, why is the function the function is a little bit complicated because it's got these modulus signs. But what's simpler about the function between 0 and pi over 2? So between, well, if t is in the interval 0 and pi over 2, what can I say that f of t is equal to? Well, because sine t is positive and because cos t is positive, I can just get rid of those modulus signs. Okay, and now we're just back in the old-fashioned world of trigonometric functions, sine t plus cos t. Okay, now is there a nice way of writing sine t plus cos t? Well, if I use harmonic form, you should have this at your fingertips. This is the same as sine of t plus pi over 4 times root 2. So I've just done the harmonic form. I've written it as root 2 times 1 over root 2, 1 over root 2, and then done the addition formula. What I now want to look at is I want to look at when does f of t equal 0? Well, sorry, equal 1. Well, that happens when root t sine t plus pi over 4 is equal to 1, which happens when sine t plus pi over 4 is equal to 1 over root 2. And that happens when t plus pi over 4 is equal to arc sine 1 over root 2, so that's pi over 4, or whole multiples thereof. Or when t plus pi over 4 is pi minus pi over 4, which is 3 pi over 4 plus 2m pi. So what we've got is that f of t equals 1 when t is 0, or when t is equal to pi over 2. But what we've also shown is that it's not 1 anywhere in this interval. So no smaller number than pi over 2 could be a period. So pi over 2 is the fundamental period. Okay, so therefore the period is not smaller than pi over 2. Okay, any comments, questions, queries about that question? Is everybody happy to continue? I'll just wait for some thumbs up just to reassure myself that everyone is alive. Yeah, good. Yeah, some thumbs up coming through. So there was a question which says, is there a way of doing it without sketching it? Now, if I just look at my screen, if you look at, I'm just trying to think of the best way of highlighting it. But if you look at this section here, this section in here is the section which showed that pi over 2 is a period. Okay, and this section over here, and I'll just highlight around it. This is where I showed that pi over 2 is the smallest period, or no number smaller than pi over 2 is a period. And what's interesting is that I never actually used this sketch. So on some level, the answer to your question, Mia, is there a way of doing it without sketching it? Well, yes, you just do the green working and the yellow working. Okay. Me personally, okay, now you might have some insight that I don't have, is without drawing the sketch, I can't picture myself being confident that pi over 2 was a period, was the smallest period. And I could picture myself falling into error and thinking that maybe pi was the smallest period or 2 pi was the smallest period. So the sketch wasn't strictly necessary, but having drawn the sketch, the way the picture came out, with this down bit and this down bit being the same, and this up bit and this up bit being the same, gave me a sort of insight and an intuition that pi over 2 was going to be a period. So the sketch was not necessary, but I certainly found it helpful. If you guessed pi or 2 pi, would the yellow section not show that it is pi over 2? No. Okay, because all the yellow section has done is the yellow section has only shown that for the first time that it's 1, or sorry, the second time that it's 1 after 0 is pi over 2. But the yellow section doesn't guarantee that pi over 2 is a period. It just shows that the period can't be shorter than pi over 2. The yellow section on its own doesn't rule out that the function looks like this, but then does some, you know, it could do this and then this, in which case its period would be pi and not pi over 2. Okay, so you would have needed to have done the green section, but in a sense you'd only have done the green section if you'd done that pi over 2 is a period. If you'd guessed that pi was the period, then you could have done an equivalent green section which would have shown that pi was a period, but you'd still be left with work to do because your yellow section would have only ruled out periods shorter than pi over 2, but would not have been enough to have guaranteed that pi over 2 was the period. So you would still be in some doubt. Does that make sense? So getting the guess right initially saved us work because we did the right green section. If you were doing this for real and you hadn't drawn the sketch, you might have guessed pi was a period, done some work, then only got that pi over 2 was like the first time that was 1, and then maybe thought, oh, well, maybe pi over 2 is the period, and then redone the green section. But that would have been more work overall, probably, than drawing the graph. Okay, let us continue. Okay, so we'll do a MAT question. We'll do a MAT multiple choice question. So MAT, as people will know, is the maths entrance paper for maths. So we'll just do this in the chat. So it says the graph of y equals sine squared root x is drawn. And which one is it? Is it A, B, C, or D? And I'll just give you a minute to put those into the chat. Okay, still waiting for things into the chat, which is fine. Okay, so let's have a think. So firstly, the function is sine squared of something. So I'm going to say straight away, I can rule out A. Okay, why can I rule out A if the function is sine squared of something? Well, I'm just trying to see if anyone's super speedy typing into the chat, but a squared function is always greater than 0, and A goes negative. I'm also going to say that I can rule out C, okay, because C has got maximums of different heights. Now, as root x increases, okay, sine is just going to do a complete sine wave, but sine is always going to go up to the same maximum. Okay, so we should always go up to the same maximum. We should always go up to a maximum of 1. Okay, so at the moment we're between B and D because they both go up to the same maximums. Now let's try and get a feel for which one it is between B and D. So a nice thing to think about is where these zeros should be. Okay, so let's have a think about when does sine squared root x equal 0? Well, that's the same as saying that sine of root x is equal to 0. But when does the sine of a argument equal 0? So the sine, if sine of root x equals 0, what can I say about root x? Yeah, it's n pi, because if I think of my normal sine, my normal unchanged sine wave, it's got zeros at 0, pi, 2 pi, 3 pi, 4 pi, and so forth. So root x needs to be a multiple of pi, so I'll just write it as n pi. And then when I square, x is n squared pi squared. So the first 0 should be at pi squared. The next 0 should be at 4 pi squared, so the next interval should be longer. Now in D, the intervals are all sort of evenly spaced. Okay, so I can rule out D because the intervals are evenly spaced. What I really want is graph B, where the zeros are getting further apart. Okay, so the correct answer was B, and I'll just go into the chat. Okay, so there was quite a lot of people that thought it might be D, and then people started to change their answer to B. Okay, question number 6. Which of the graphs below is a sketch of y equals 1 minus 4x minus x squared minus 5? And I'll give you a minute or so to, well, I'll give you a little bit longer or so to put that into the chat. But what I'd also like you to put into the chat is a suggestion of the best way to write this quadratic denominator. So give me a suggestion of the best way to write the denominator, then have a go at then try and do that, and then try and pick out the graph. So I'm just going to wax lyrical about the method. So I want what will really help me is if there was some easy way of determining where the maximum or minimum was and whether there is a maximum or a minimum. Now, I don't really want to differentiate, because if I differentiate, I'm going to get a horrible quotient rule, which I'm not going to particularly like. So is there a way of writing a quadratic which gives me a great insight into where its minimum to be? Well, the first thing I'm going to do is I'm going to rewrite the numerator. I'm just going to change the sign of the numerator. So I'm going to write the numerator as x squared minus 4x plus 5. Now, which format of writing a quadratic is going to tell me straight away where the maximum or minimum is? Well, that's going to be the complete squared form. So I can write x squared minus 4x plus 5 as x minus 2 all squared plus 1. Remember that I flipped the sign. So my y is negative 1 over x minus 2 squared plus 1. So first of all, having written it this way, why can I rule out the top two graphs? What can I say about the sign of my y? Well, the denominator is something squared plus 1, so the denominator is going to be positive. So the overall function is going to be a negative number over a positive denominator, so the function is going to be negative. Okay. Now we need to find a turning point. So when is the denominator going to have an extreme value? The denominator is going to have an extreme value when the denominator is minimum, and the denominator is minimum when x equals 2. Okay, so when x equals 2, the denominator is going to be least negative, so the absolute value will be greatest, so there'll be a turning point at x equals 2. So we're looking for the one which is got a turning point to the right of the origin. So the correct answer is C. Yeah, you could differentiate it. Yeah, I mean, but I think the complete square form is clearer. Okay, are people happy with those math questions? I think I'll leave the next multiple choice math question and now tackle a long step question. Is everybody, sorry, a long math question. Is everybody's got mental stamina to continue? Yep, good. So, and obviously if you're watching this on catch up, you know, I would probably recommend pausing the video at this point and trying the math question on your own. But here it goes. So it says, in this question, we will consider the function f of x defined by f of x equals x squared subtract 2px plus 3, where p is a constant. It then says, show that the function f of x has one stationary value in the range 0 less than x is less than 1, if 0 is less than p is less than 1, and no stationary values in that range otherwise. Okay, quite a lot to read and quite a lot to digest, but what are people's instinct about what we should do in order to find the position of the stationary value? How do you find where the stationary value of a function is? Yeah, so let's differentiate. So we've got f dash x, and that is equal to 2x subtract 2p, because we've just got a quadratic. And f dash x is 0 when x equals p. Okay, and I think it's always a good idea to get some feel for the shape of the curve. If I consider my expression for f dash x, if I consider 2x subtract 2p, If x is less than p, then that expression for the derivative is negative. If it's greater than p, then it's positive. So f of x has this shape. In fact, I could have known that f of x had that shape because x squared subtract 2px plus 3 is a positive quadratic. Okay, so we know that it's like a U-shaped. So where is the stationary value? Well, the stationary value of f of x is at x equals p, and that's value of p is only going to be between 0 and 1 if p is between 0 and 1. Okay, so the stationary value of f of x is at x equals p, and this is in the interval 0, 1, if and only if p is in 0, 1. Okay, what next? So part I, for all its complicated sound, was actually really, really easy. We just needed to find the turning point of a quadratic, so find the minimum of a quadratic, and then decide if that turning point was in 0, 1 or not. That in the remainder of the question, we will be interested in the smallest value obtained by f of x in the range between 0 and 1. Of course, this value, which we will call m, will depend on p. So part II, if p is, it says show that if p is greater than or equal to 1, then m equals 4 subtract 2p. So if p is greater than or equal to 1, what can you say about the function f on the interval 0, 1? Okay, so for part II, we have p is greater than or equal to 1. And it's probably worth drawing a sketch. My f of x has got some minimum at p. P is greater than 1. So what can you say about the function f on the interval 0, 1? So if p is greater than or equal to 1, then f is doing what on 0, 1? I'm just going to see if anyone's put that into the chat. Yeah, it's decreasing. Okay, and this sketch I think is really, really helpful because this sketch shows me that the gradient is negative if we're to the left of p. So if p is greater than or equal to 1, then f is decreasing on 0, 1. And if it's decreasing on 0, 1, and the minimum is obtained at f of 1. Sorry, my handwriting is getting a bit scruffy on the screen. But f of 1 we can find by just substituting 1 into f of x. So that's 1 squared subtract 2p plus 3. And so f of 1 is 1 subtract 2p plus 3, which is equal to 4 subtract 2p. For III, what can we say about the function f of x if p is less than or equal to 0? Well, if p is less than or equal to 0, we've got a very similar sketch. So here the turning point is to the left of 0. And so the function on 0, 1 is increasing on 0, 1. And the minimum is obtained at f of 0, and f of 0 is really easy to find because that is just 3. And now part IV, so the fourth part, so the final case, 0 is less than or equal to P is less than or equal to 1. Where is the minimum? So in this case, my diagram is going to look like this. P is going to be between 0 and 1. And what did we decide was the position of the minimum? So in this case, the minimum value is just f of P, because we've shown that the minimum of the global minimum of f is obtained at P, and f of P is P squared subtract 2P times P plus 3, which is 3 minus P squared. Notice there's some subtlety in this question because P morphs from being a parameter in F, so a constant, to now being a variable when I'm considering M. So overall, M is now a function of P. So M is a function of P. And we've shown that M is equal to 3 when P is less than or equal to 0, is equal to 3 minus P squared when P is between 0 and 1, and is equal to 4 minus 2P when P is greater than or equal to 1. And then the final part of the question asks us to sketch M as a function of P. And I think we should be able to do this in the chat. So this first part here, so I'll just highlight it, M equals 3 when P is less than or equal to 0. What does if a function is just equal to a constant, what's the graph going to look like? And that's in the chat, it's just going to be a flat line. Excellent. Okay, so when P is less than or equal to 0, we're just a horizontal line, and this is at height 3. Next part of the curve, so again, put it into the chat. 3 subtract P squared. What type of curve is 3 subtract P squared? Yeah, an inverted U shape. Oh, not hyperbolic. If we've got a P squared term, what do we call the graph of something which has got a P squared? Yeah, it's a parabola. Yeah, so it's just a parabola. And now notice that the parabola and the line meet, because when P equals 0, 3 subtract P squared is 0. So we've got a parabola coming down. Oops, I'll do it in my black pen rather than my highlighter. I've just turned dotted because it's only a parabola between 0 and 1. Okay, so this section here is the parabola. I mean, if it was continuing, it would be that dotted line, it would be my upside down U, but this is 3 minus P squared. And this is Y equals 3. So we've done the blue section, which is a flat line. We've done the yellow section, which is an inverted parabola. And then the final section, 4 minus 2P. What sort of curve is 4 minus 2P? Someone put that into the chat. Yeah, it's just a straight line. Okay. Notice when P is 1, 4 minus 2P is 2, 3 minus P squared is also 2. So the line is going to hit where the curve is. In terms of the line 4 minus 2P is definitely going down, but there's all sorts of ways it could go down. It could be this, it could be this, this. How would I, decide whether it was option 1, option 2, option 3, what might be worth looking at in order to get an accurate sketch? Do you understand what I mean? Because although I know it's a line, I don't know if it's a very shallow line. I don't know if it's a very steep line. What might help me get? Yeah, so I could look at the root. Good. So I can see that 4 minus 2p is 0 when p equals 2. 3 minus p squared is going to be 0 when p is square root of 3. So it's certainly, I can rule out 1 because it should be to the right of that root. What else might be worth looking to see how it sort of meets? Yeah, to look at the gradients. Okay, because the gradients will sort of be able to tell me whether it sort of, whether there's a kink in it, whether it gets steeper or less steep. Now, the gradient function of 3 minus p squared is minus 2p, and at p equals 1, that is equal to negative 2. The gradient of the line is also negative 2. So the gradients are the same. So if the gradients are the same, how is that line section related to the curve? What do you call a line which touches a curve but temporarily has the same gradient? The tangent. Excellent. Okay, so I can get rid of these lines. The line that we want, the black line, is the tangent. So it's got the same gradient. So it'd be the same as the tangent line. So if I sort of do the same thing of dotting, it would be the tangent, and it meets at this point here too. Okay, so my sketch has got a flat bit, a parabolic bit, and then this bit is a line. Okay, any questions about that? Any questions about that Matt question? Okay, I've got a quick question for Vlad, if Vlad is around. What, or Dr. Chernov, what time do these normally finish?
Hello, yes, we normally finish at past.
We normally finish at past. Excellent. So I've got 7 minutes to do the final step question. That might be a little bit of a scamper. Obviously, if you think in a real step exam, which is 3 hours, you're doing well if you get 5 questions. 6 questions is the maximum possible. So this question should take half an hour. So 6-7 minutes is going to be a little bit of a scamper. Before I do that, does anybody have any questions? Super. Okay, give me a thumbs up just to reassure me that you're all there, and then we'll have a look at this step problem. Okay, and I think you'll probably see rightly that step is just that little bit more intense than math. So it says, show that for 0 less than or equal to x less than or equal to 1, the largest value of x to the 6 over x squared plus 1 to the 4 is 1 over 16. Put it into the chat. What do you think would be the most natural thing to do first to enable me to decide on the maximum or the largest value of this function? Differentiate. Excellent. And so I'm going to differentiate using the product rule. So that is v times du minus u times dv all over v squared. And I can simplify, I can cancel an x plus 1 cubed top and bottom. I can take out a factor of x to the 5, so I get, and a factor of 2, so I can take out 2x to the 5 which gives me an extra x squared plus 1 times 3, and then take away 2x all over x squared plus 1 to the 5. Sorry, this is x squared plus 1. And I need an extra x in the derivative, don't I? Because, oh, no, wait a minute, I need an extra 2x in the derivative. Because when I differentiate x squared plus 1 to the 4, I pull out a 2x and a 4. So this is an 8. And this is an x. And so this is take away 8. That's x7, so that's take away 8x squared. Okay, are we happy? Oh, and then when I've factorized out the 2, I get a 4x squared. And so this all becomes 2x to the 5. 3x squared take away 4x squared is take away x squared. And then I get 3 take away x squared all over x squared plus 1 to the 5. Doing this live is relatively terrifying. Okay, what can you tell me about the sign of the derivative between 0 and 1? So for 0 is less than or equal to x is less than or equal to 1, this bracket is positive. This bracket is positive because x squared is less than 3, and the bottom bracket is all positive. So we've got y dash is bigger than 0, so y is increasing. My pen is ridiculously thick. So the maximum okay, so the maximum, if the function is increasing, what value of x does the maximum occur at? At x equals 1. Excellent. And at x equals 1, y equals 1 to the power 6 over 1 squared plus 1 to the power 4, which is reassuringly 1 over 16. Okay, the next bit is probably where I'm very, very glad that this finishes at 7:30, because that means that I'm probably just going to be able to delegate this a little bit. But it says find constants a, b, c, and d such that for all x we have this identity. So all we would need to do here is differentiate by the product rule and find the equivalent and find the appropriate values of a, b, c, and d. So I'll try and do that very, very quickly, but feel free to go if I go a little bit over. But we do v du, so my right hand side is v, which is x squared plus 1 cubed, times the derivative of that polynomial, which is 5a(x4) plus 3bx squared plus c. Take away u, which is the original polynomial, times the derivative of x squared plus 1 cubed, which is 2x times 3, so that's 6x, x squared plus 1 all squared, all over x squared plus 1 to the 6 plus dx squared over x squared plus 1 to the 4. And then we can pull out an x plus 1 squared. So we get x squared plus 1, 5a(x4) plus 3bx squared plus c minus 6x, well, 6, and then a x to the 6 plus b x to the 4 plus cx. Sorry, this is x squared, because I've got an x in there, plus d all over x squared plus 1 to the 4. Okay, and in the interest of time, I won't do the calculation. Yes, I did miss an x. Okay, but I put it back in. Okay, you will now, if you were to expand here and equate coefficients, you would get simultaneous equations that allowed you to find A, B, C, and D. In fact, there's only one. C is going to be easy to find because there's only one units term. Okay, there's only the one hitting the C. So C must be 1. To find out what B is, I would then need to look at the terms which end up making an x squared, which is going to be the 3b, take away the 6c. Okay, but anyway, we can find A, B, and C. Okay, which I will leave as an exercise. Options for suggestions for what to do in the last part. Okay, so let's imagine we found A, B, C, and D. Talk me through how you would now be able to do this horrible integral. So let's imagine we have this decomposition. So we're trying to integrate between 0 and 1 d by dx of something plus dx6 over x squared plus 1 to the 4 dx. Now this looks scary, okay? And this is why, this is what step is meant to look like. Step is meant to look scary. But can anyone see anything which shows that this is nowhere near as scary as it looks? Why is this first integral, which is the scariest looking one of all, why is this integral laughably easy? What very straightforward thing are we doing? Yeah, so the first integral, so this one where we're integrating the derivative, why does that just disappear? What happens when you integrate a derivative? Yeah, exactly. The moment you're integrating a derivative, you know that the antiderivative is just the function that you differentiated. So this first part is just going to be ax to the 5 plus bx cubed plus cx evaluated between 0 and 1. Now and this is where it's really useful to get a little bit of psychological kind of reassurance. Looking at the question, what do you think that integral is going to be? In terms of looking at what we're trying to prove, what numerical value would come out to reassure you that you'd found A, B, C, and D correctly? Yeah, 11 over 24. So this bit is going to be the 11 over 24. Now the second part, this x squared over x squared plus 1 over 4, will turn out to be something that we can't integrate. This is why we get the inequalities. But what did we show about that function at the beginning? We showed that that function is some function that is going to live between 0 and 1 over 16. And it's an increasing function, so I've drawn it right. So what can you tell me about the integral between 0 and 1 of x to the 6 over 1 plus x squared all squared? We know that the function looks like this. The integral is the area. So the area is going to be somewhere between 0 and the area that you would get if you just took the whole rectangle, which would be 1/16. So the integral of this part is going to be somewhere between 0 and 1/16. And so that's where this part of the inequality comes. Okay, so that actually worked out quite well, being short of time, because it means that I haven't done every single step. But hopefully, you know, I've broken the back of this step question and turned it into something which is no longer scary. Okay, all that's left for you to do is to find the values of A, B, and C, A, B, C, and D. Well, I think that D is going to be 1 because that's where this 1/16 comes from, and end up with something which evaluates to 11/15. Okay, so that's a very nice question using maximums and minimums of functions in a non-standard way inside an integral that looks impossible. One tiny little thing which I'll give away, which I won't give away, but if you want to do extra special research, it turns out that this integral 1/x² plus 1 to the 4, if you put it into Wolfram alpha or something like that, will actually give you an integral that involves pi. And this method will end up giving you a very good rational approximation to pi. It'll actually end up with an approximation to pi that is approximately the famous 22/7, and then it will also give you an upper bound based on that. Okay, so I've run a tiny little bit over. I hope, Vlad, that that's not too horrific and that people don't
Absolutely, absolutely not.
Yeah,
I frequently run over.
Okay, good. So I'll just actually look, just to sort of tantalize you, I'll just pop into Mathematica and I'll just integrate 1/x² plus 1. What was it? All to the power 4. And I'll do that between 0 and 1. That turns out to be the exact value of that integral. This is just to tantalize you. Turns out to be 11/48 plus 5 pi/64. Okay, and I'm fairly certain that if you rearrange that, you'll get the 22/7 estimate for pi. My daughter's just come into the room to ask me when I will be done. I think the answer to that is very, very soon. Does anyone have any final? Questions? No? Oh, how do you know that you? How do you know that? So there's a question which says, "How do I know that I can't integrate it? Which bit?" Oh, the function that I put into Mathematica. So this integral 1/1 plus x² to the 4 dx integrated between 0 and 1. I know how to integrate it, and it's a function which, when you do further maths, you will learn how to learn how to integrate this. The fact that you get a pi coming in as an integral means that this integral actually ends up involving trigonometric functions. Okay, in particular, it ends up using inverse trig functions. And I think it'd be wrong in this context for me to sort of, you know, show you exactly like why and to show you the inverse trig functions that are involved, because that would just spoil another problem later down the line. So this function here you can do, but it involves inverse trig functions, and that's why you end up getting a pi. Okay. Obviously, this function at the end, this x6 over x squared plus 1 to the 4, again, this decomposition tells me that I can integrate it because I know how to use integrate 1 over x squared plus 1 over 4 using trig functions, and then it's different from that, from a derivative of a function. So this x6 over x squared plus 1 to the 4 will just have like more complicated trig functions in it. Okay, it turns out that all rational functions of this type, which have got like a that every rational function, so if it's got polynomials on the top, polynomials on the bottom, you can always integrate them if you know how. So you can do things like splitting them into partial fractions, which will give you integrals involving logs, and then splitting them into parts which have got irreducible quadratics on the bottom, which will involve inverse trig functions. What's also true is that you can extend this method by getting similar estimates for the integral of 1 over x squared plus 1 to the 6, or 1 over x squared plus 1 to the 10, or 1 over x squared plus 1 to the 20, to get better rational approximations for pi. Okay, so this question in some sense sits a little bit between step 1 and step 2, because it kind of does all the work, but it loses what would be a nice punchline, that this ends up with a rational approximation for pi. I hope that answers your question. Let's have a look at the chat. No, it's not. Yeah, it is substitution. It's not tan to the 4. I mean, I don't want to spoil it too much, but let's think about a substitution. You would want to maybe try and think of what could x equal. So can you think of setting x equal to something so that 1 plus something squared was going to be a nice function that you might be able to end up integrating? So is there any identities that you know where 1 plus something squared is equal to something nice? And this would, and again, I don't want to tell you the answer because I'd get in trouble with your further maths teachers at some point, because I'd spoil a nice bit of maths. But if you were looking for a substitution, this would be the substitution that you'd be looking for. Okay, any other final questions, or can I go and play with my daughter? 1 plus tan squared equals sec squared. Play with it. Okay, so if x equals tan theta, 1 plus tan squared theta is indeed something nice, it's sec squared theta, then think what you'd need to do to the dx to go from an x integral to a theta integral, and play around with it. As I say, I don't want to spoil it. I don't want to spoil it too much, but see if this, this is a substitution which on the surface looks like it'd be quite nice, because one thing which is quite nice, because you're doing the reciprocal of 1 plus tan squared, you'd end up doing the reciprocal of sec squared theta, which would just give you a nice respectable cos squared theta. Anyway, I better be quiet there before I really spoil it for your further maths teachers. Okay, any other questions, comments, observations? People are saying nice things.
Yes, thank you very much, David. This I really enjoyed it, and I hope the students as well.
Great. Well, I'll print off the I'll turn the OneNote into a PDF. I'll send that to you to distribute to the other students who didn't make it. And I hope you've enjoyed the evening.